Okay, everything's set up on YouTube. I think we can get started as people start pouring in. So I'll just give you a brief introduction. Hello, everyone. Welcome to another talk in our webinar series. This webinar is also being streamed live on YouTube. You can find the link on our website or access it on our YouTube channel. That's Linea MCTI. Today, we have the honor of having Dr. Marla Geha from Yale University. Dr. Geha is a professor in both the astronomy and the physics department at Yale University, as well as the director of Yale Telescope Resources. Her research focuses on the formation, evolution, and destruction of dwarf galaxies with the goal of using these objects to answer fundamental questions in astrophysics and cosmology. Her current work includes observations of ultra-faint galaxies recently discovered in the local group. Dr. Geha, thank you so much for being so kind and having accepted to give us a webinar talk today on such an exciting topic. The floor is yours.
Thank you. I am delighted to be talking with you today. We were actually just talking earlier about how exciting time it is to be doing astrophysics. I have just started looking at some JWST data. I'm on one of the early release teams, which is just absolutely beautiful data. LSST Rubin is going to be turning on soon. And so there's just, it really is a fun time to be doing astrophysics. What I wanted to chat with you about today is a project that I've been working on. It's a long-term project. So we've been doing this project for about 8 years, and we are just finishing up the final results actually this summer. This is the Saga Survey. It's a small team, so Yaoyun Mao and Risa Wexler are my main co-PIs, and really everyone on the survey is on this slide. We are interested in better understanding our Milky Way by placing it in a cosmological context. And so half of my research, half that I won't talk about today, is studying the Milky Way and the Milky Way satellite galaxies in real detail. And in order to better understand the context of those sort of studies, we want to understand the Milky Way satellite galaxies, sort of how they fit in, are they outliers, and whether what we learned from the Milky Way itself, how to better interpret those data. What do I mean by satellite galaxies? So let me just kind of zoom, let's see if I can, there we go, zoom in to these images. So when I say satellite galaxies around the Milky Way, in this context, in the Saga Survey context, what we're saying is satellites that is small galaxies that are within the virial radius of the Milky Way, and I'll define that in a little bit. And because we are looking at systems that are beyond the Milky Way, so we're going to be looking at systems that are sort of 20 to 40 megaparsecs away, we're really focusing just on the brightest satellites. So in the context of the Saga Survey, where we're going to be looking at about 100 Milky Ways, we're talking about satellites that are down to sort of Leo 1 or so. So Magellanic Clouds, Sagittarius, Leo 1. So in this context, Milky Way would have about 5 or 6 satellites. Why are the satellites interesting and why are they important? So this is a cartoon of the brighter Milky Way satellites. There are currently something like 60 known satellite galaxies around the Milky Way. Maybe there's 63, 64, depending on how you count. Proximity allows us to study these satellites in great detail. So we can get individual stars, we can get their metallicities and their kinematics. And they provide us a super strong test, both for cosmology and for galaxy formation. So for example, in terms of cosmology, we can better understand the dark matter profiles, the density profiles in these satellites. We can measure them using individual stars and compare those to theory. The satellites are also very clean places to search for dark matter annihilation. So that is looking for signs of gamma rays in these objects. And some of these tests are generic to the Milky Way, and some of them are less generic. So for example, if we see dark matter annihilation in a dwarf satellite around the Milky Way, that says something very generic about dark matter. Other tests are less generic. So for example, if I'm measuring star formation histories of a Milky Way satellite, it is tempting to assume that those star formation histories are generic to a low mass galaxy. However, if there is something strange about the Milky Way, something about its formation history or something like that, we may be led down the wrong path, or we may be making inferences that are much more specific to the Milky Way and are not generalizable to galaxy formation. And so that's what we wanted to do, is think about those more generic tests and try and put the Milky Way in a bit more context. So let me just kind of break the questions that I will talk about in this talk. So again, breaking these into cosmology and galaxy formation, the question that I'll focus on today on the cosmology side is, what is the nature of dark matter? So that's the question. On the galaxy formation side, the question I want to try and address is what processes quench star formation in low mass galaxies. So those are sort of the two big questions. The tool that we will use to answer this first question is just looking at the ratio of the number of satellites around a Milky Way-like galaxy. So a very specific question. And so how do we do this? How do the number of satellites tell us something about the nature of dark matter? So in a cold dark matter simulation, the number of satellites around a large galaxy is fairly well defined. We can predict that. If we turn and look at an alternative dark matter, so let's say this is an extreme case that's already been ruled out in other ways, but let's say we were looking at a warm dark matter simulation. In this case, the warm dark matter particle, actually, I forget, I should have written that down. It's, I think it's a KeV or so. It is ruled out by other observations, but just for an illustration here, these are two similar simulations. But then if you go and circle where the galaxies are at redshift 0, the large galaxies are relatively the same. And so if you look at the large circles in both sides, the large circles are the same, but it's the small galaxies that are very, very different. And so by just counting up the ratio of satellite galaxies around a Milky Way, we can say something fundamental about dark matter. Going over to, so the observation will be just counting up satellites around a Milky Way analog. On the galaxy formation side, asking questions about how stars form and how star formation is quenched in low mass galaxies. To answer this question, we can first look at the Milky Way's population. So in the Milky Way, the two brightest satellite galaxies are star forming. So the Magellanic Clouds, which we think are on first infall, are both somewhat actively forming stars. And then every other satellite lower mass than the Magellanic Clouds are quenched. And we believe that those things have quenched at least a gigayear ago or more. And so in the Milky Way, 2 of the 5 brightest satellites are, 3 of the 5 are quenched, 2 of 5 are forming stars. And that's true in M31 in Andromeda as well, that the majority of satellites, the majority of bright satellites are quenched. And so in M31, 3 of the brightest satellites are forming stars and the rest are not. I can illustrate that a little bit more if we look at the gas fraction in satellites around Milky Way and M31. So if a galaxy has gas, that's a proxy for active star formation. This is a really lovely plot by Mary Putnam. This is the distance on the x-axis from a satellite from the Milky Way or from M31, depending on which is its primary. And the y-axis is either the gas detected or the upper limit on the gas fraction. And so down at the very bottom here at 0, 0, there are gas fractions for the faintest satellites that are not detected, and the upper limits are like 15 solar masses of gas, so truly quenched galaxies. And you'll see there are very few filled in circles. That is, there are very few detected satellites with gas in the local group system. And I'm adding Magellanic Clouds here. They actually go off the y-axis. So there's only a handful of galaxies that have gas detections in the Milky Way. And so we can look at the ratio of star forming to quenched galaxies in systems beyond the Milky Way, just to see whether or not the Milky Way is a typical system, and the things that we infer from star formation in those satellites, whether or not it's a typical thing. So we'll look at the quenched fractions between these. And so these are 2 science questions. They have been answered in the Milky Way. And let's see if we can answer them in a more general, more statistical way. And to do that, we need to look at, oh, sorry. So the Milky Way is, it's just a single realization. And so let's understand these questions in a more general sense around a Milky Way mass halo. And so the first question there is, how do we even define a Milky Way? We will define a Milky Way a couple different ways. So first, we will define the satellites as being within the virial radius of a Milky Way. We'll define the virial radius of a Milky Way as about 300 kiloparsecs. We will also require that there are no galaxies that are the Milky Way size or more massive within that virial radius. That is, that's an environment cut, so that there are no massive galaxies within the virial radius of that Milky Way. In that, with that definition, the Milky Way and Andromeda are two separate systems. There are some orientations we could see the local group where we would have thrown the local group out. But for most orientations, the Milky Way and Andromeda would both be in our survey. And then, let's see, so it's the virial radius. We will also define the Milky Way based on a luminosity. So we will assume that the Milky Way is defined based on a halo mass, a dark halo mass, and then we'll ask in simulations, what is the range of stellar masses that could live inside of a dark matter halo that has the mass of the Milky Way? And so the luminosity range we define in K-band, which is a good proxy for stellar mass. And it's about 1.5 magnitudes range that we'll define in luminosity. Again, we will define an environment cut, making sure that these things are outside of major groups and don't have a bright galaxy inside of its virial radius. And so with that definition, we can then make some decisions about what distance range we're interested in. So let me talk about what distance range we're interested in and why we chose the distance range we did using this next slide. So in the Milky Way, we can detect a satellite looking at, we can see a satellite by looking at individual stars, and we can measure its distance based on fitting an isochrone to a CMD. At the other extreme, so we're doing resolved stars, the Milky Way M31, it's like 60 satellites, 30 in M31. On the other extreme, the Sloan Digital Sky Survey got spectra for everything and found Milky Ways out to, using its magnitude limit, we can find Milky Ways out to about 200 megaparsecs and a satellite down to about LMC. So with the Sloan Digital Sky Survey, we found satellites using spectroscopy, complete spectroscopy, getting spectra of everything. And the magnitude limits means that there's only about 1 satellite per host. The Sloan results are very interesting. And actually the Sloan results were what motivated the Saga survey originally. So if you just look at the satellites that Sloan detected, it was able to find LMC SMCs. And if we just ask, given a Milky Way, the way we defined a Milky Way, how many satellites are around a Milky Way like that? The Sloan results suggested that the LMC are slightly unusual. That is, most Sloan systems have just a single satellite that are of the luminosity LMC SMC. So the Milky Way having 2 satellites is a bit unusual, but it's not that unusual. It's a 4% chance. So, it's possible. It's well within the sort of the limits that you might expect. If we want to get more satellites, so if we want to push down below LMC SMC, we need to do one of 2 things. First, we need to either get full spectroscopy for everything. That's currently beyond our resources, although DESI is absolutely going to be able to push full complete spectroscopy down another few magnitudes. But if we don't want to wait for that, there's been some fabulous work in the local volume within about 20 megaparsecs using surface brightness fluctuations to determine distances to satellites. And so here, surface brightness fluctuation or tip of the red giant branch to determine whether a galaxy is a satellite of a Milky Way. Here, they're able to detect something like 5 to 8 satellites per host, but they're somewhat limited within 20 megaparsecs. There's only a few tens of systems that are like the Milky Way. So they're able to find satellites around Milky Way-like hosts, but they don't have a large number of hosts to work with. The results from these simulations are really quite interesting. So for the most recent results, so this is from 2021, luminosity functions for 6 Milky Way analogs, pushing down to an absolute luminosity of -9. These are the plots I'll show for all 6 of these Milky Way analogs. Here's for the Milky Way. So what you're looking at here is the cumulative luminosity function. Bright is on the right, fainter is on the left. The red is the data. So this is the cumulative number of satellites. And then the blue is 1,000 realizations of a Milky Way-like halo with the survey parameters. And you can see the Milky Way is a bit unusual. It's kind of outside the 1 sigma contours for what's predicted. M31 a little bit more, but these really low statistics. Here are the results for those 6 Milky Way analogs. And you can see that, first of all, there's quite a diversity. The red lines are sometimes above the prediction, sometimes below. And it's really difficult to quantify whether or not these 6 or 8 systems are consistent with the predictions or not. We really need to have more statistics to really quantify the scatter in the luminosity function. And so putting this together, a question we might ask is how many Milky Way analogs, at least to answer this question, what is the scatter in this luminosity function? How many Milky Way analogs are really needed to quantify the scatter and understand whether or not a Milky Way-like galaxy has the same number of satellites as predicted in numerical simulations? And so this simulation has 1,000 realizations. So these gray lines, there's 1,000 gray lines. And so we don't need 1,000 of these to quantify the scatter, but we need something more like 100. 10 is definitely too small. 1,000 is certainly overkill. And so we wanted to focus on something like 100 Milky Ways in order to answer this question. And here's where the problem comes in. If we want to look at the luminosity functions, the satellite luminosity functions around 100 Milky Ways, we need some sort of technique that allows us to probe a volume such that we can get 100 Milky Ways. That volume is larger than what we can currently do with surface brightness fluctuation or tip of the red giant to determine distances. And so that's where this Saga survey comes in. So the Saga survey is probing Milky Way analogs between 20 to 40 megaparsecs. In this volume out to 40 megaparsecs, we have access to something like 100 to 150 Milky Ways. We can't do surface brightness fluctuations to determine distances. At the same time, we don't have resources to do complete spectroscopy of all of these hosts. And so what we have done is tried to do targeted spectroscopy to determine the satellites and the satellite luminosity functions around these systems. And so the Saga survey's goal is to characterize satellite populations around 100 Milky Way analogs down to our resources, our limits of about -12, which is a stellar mass of 10 to the 7th or so. Before I turn my attention fully to Saga, I just want to say that the local samples and the more distant samples are really important complements to really understanding the questions that I posed at the beginning of the talk. So the Saga survey, if we want to probe out to about 30 megaparsecs, at 30 megaparsecs, a Milky Way's virial radius, 300 kiloparsecs, is the equivalent to a diameter of about 1 degree on the sky, which is huge, right? That's twice the size of the full moon. At 30 megaparsecs, if we want to probe down the luminosity function down to below the large magnetic clouds, down to about -12, that's equivalent to an apparent magnitude of R of 21. Within a degree, there are several thousand galaxies down to an R of 21. And here's where the observational challenges come in. So here is an image, just a catalog image. This is RA and DEC of a typical galaxy in the Saga Survey sample. The blue are every galaxy down to R of 21. And there's about 2,000, 2,500 galaxies per square degree. Where we're going is trying to find spectroscopically confirmed satellites around this object. And there are only about 4 objects per square degree. And so we don't necessarily want to get spectra for absolutely everything, because this would be an incredibly inefficient way to do this. Several years ago, when we were starting out, we were very limited. We didn't want to get rid of any satellites. And so we could only do fairly coarse color color cuts, color criteria, to get rid of galaxies that we were absolutely certain were higher redshift than 40 megaparsecs. Doing those safe color cuts, we were able to reduce the target density down to about 1,000 objects per square degree. And indeed, in 2017, we published our first results for only 8 Milky Way analogs doing these color cuts, where we just got a lot of spectra, and it was very inefficient. We have learned since 2017, and we have learned how to select out galaxies that are confidently low redshift down to about our target density of 200 square degrees. And we don't actually have to do better than this, because the telescope resources that we are using usually, and I'll talk about this in 2 slides, are multi-fiber spectroscopy, where we have about 200 fibers per square degree. So once we're at this point, we can efficiently target an object. Now, you may be thinking, why is this so difficult? Why do you have to get spectra for everything? And so we will do a little game. So here are images of galaxies around our Milky Way hosts. On the top panel and on the bottom panel, there are both satellite galaxies of this particular Milky Way and galaxies that are much farther distant, that are background galaxies. And as you look at these images, they look very similar. And at least by eye, it's very difficult to determine which is a satellite and which is not. And so here I will allow you for a second just to look at these images and guess what is a satellite galaxy and what is a distant galaxy. We'll do it on the top first. Just for context, this is a 30 arcseconds square each box. On the top row, the 2 images over here are galaxies that are satellite galaxies at a redshift of 0.008, which is a physical distance of 30 megaparsecs. And you can see these 2 objects look very similar to these galaxies, which are much brighter, but far more distant. So these galaxies are at redshift of about 0.06 to 0.1 and are 10 times more distant than our satellites. So you can start to see where doing color cuts and those sort of things can be quite difficult. On the bottom panel, now that you've seen this, maybe you can try guessing here. I've switched where these are. So again, 2 of our satellites on the right side now, and the higher redshift objects on this side. And so it's very difficult to do, let's say, photometric redshifts or those sort of things to robustly detect satellites at these distances. And so what we do is we do the best we can, and then we get spectra for the objects that we still believe might be satellites. And so to do this, we still need fair amount of spectroscopy. We use 2 main telescopes. We're using the AAT, the 2DF multi-fiber instrument in the south, and in the north, we're using the MMT hectospec. Both of these have 300-400 fibers with large fields of view, so very well matched to our problem. Sorry, there we go. And then for galaxies that we miss, either because they're very low surface brightness or we've just, the fiber, we weren't able to get everything on, we do follow-up single slit spectroscopies, primarily with Palomar. And in the south, we've been using the SALT telescope to ensure redshifts. And so we have a lot of redshifts. And every time we have published, we make all of our redshifts available in hopes that other people can do science with the galaxies that we have not used. So just to summarize the survey, and then we'll get into results quickly. So the observational goals for Saga were designed in 3 tiers. The first was to use very simple color cuts. This is what we did a few years ago with just a small number of hosts, but many, many redshifts. This allowed us to train and to build up understanding of how to select low redshift galaxies. We then use this efficient targeting strategy. And let's see, I guess it's been a year and a half since the second stage results were published, and that's what I'll spend most of my time on. We increased the number of hosts to 36, and we have actually recently finished data taking for stage 3. So we now have data on disk for 100 Milky Way analogs. I'll show you just a teaser of these new data. Our final survey will hopefully be published by the fall. We have 102 hosts with many, many satellites. However, as we're doing sort of data cleaning right now. All of the results that I will show next hold with the much larger sample. Just to give you a sense of where these are on the sky. So all of the symbols here in this all sky survey, on this all sky plot, these are all of the Milky Way hosts. These are all of the Milky Way objects that pass all of our criteria in our distance range between 20 and 40 megaparsecs. The ones that are solid have available public imaging. The imaging that we're using is the legacy survey, so mostly coming from DES and associated surveys. And then the red symbols are those that we have complete spectroscopy for and have published. And now most of the green and blue circles have been filled in as well. Okay, so what are our more efficient targeting cuts? So here is a surface brightness versus apparent magnitude and color versus apparent magnitude. The symbols, the blue symbols, are all galaxies in several of our Milky Way hosts. The green are objects that we have confirmed redshifts and are satellites. The orange are galaxies that are at similar redshifts but are not satellites of the Milky Way. The purple lines in both plots define our main region where we try and get spectroscopy for. So we do complete spectroscopy in this region above the purple line, so low surface brightness in this region and blue in this region. And we get complete spectroscopy in this region where most of our satellites reside. However, half of the fibers that we assign are outside of this main region. And we do discovery mode to make sure that we are not missing satellites outside of our primary selection region. So half of our fibers are in the main region, half are outside to make sure that we are not missing any strange or weird satellites. Here is a very beautiful image with most of our satellites from our paper 2. You can see behind me the same objects. Just to give you some context of where our Saga satellites reside relative to the Milky Way satellite. So here is absolute luminosity on the x-axis and apparent surface brightness, effective surface brightness on the y. The orange are the Milky Way satellites. The green are the Saga satellites. And something that I am sure you are concerned about, or many people are concerned about, is making sure that we detect very low surface brightness galaxies. You can see the Saga satellites and the lowest surface brightness Milky Way satellites, at least in our luminosity range, are very comparable. If we wanted to push down to lower luminosity satellites, like say we wanted to push into the ultra faint regime, we would getting into a very, very low surface brightness regime where Saga would no longer be able to detect these, but we are above, we are only looking at the most luminous satellites, and Saga is able to get down to those effective surface brightnesses. There's a little asterisk up here next to all. This galaxy up here, this is M32. We intentionally do not go after M32s. M32 is a very compact elliptical around M31. That would look unresolved at the distance of 40 megaparsecs, and we do not target objects that are stellar in nature. So M31 will look stellar in nature, but everything else we do. Let's see. The next thing I wanted to talk about before we get into the results is just quantifying the objects that we don't get redshifts for. That is, what is our failure rate? What is our incompleteness rate? The primary incompleteness of the Saga survey is not in the photometry. That is, our photometry, we are able to very robustly detect galaxies down to an R of 21. Even the lowest surface brightness galaxies are very well detected. The legacy survey goes down to a limiting magnitude of 23 to 24 in R band. And so at the limits that we are interested in, everything really is well detected. Where our main incompleteness is coming is due to spectroscopic incompleteness. So this is fiber magnitude, but really this is a proxy for surface brightness. And the color, the way these symbols are colored is by the failure rate of our redshifts. That is, we put a fiber on a galaxy, did we get a redshift or not? You can see there's a clear bias for redshifts to fail as we go to lower surface brightness. And this, I really should have two plots here. There are many, many, many objects in each of these blue points, whereas in these red points, these lower surface ones, these are like representing 1 or 2 galaxies. But there's a clear bias in our incompleteness. While there is a bias, this is something that we can quantify for. And so it's a known unknown in the sense that we can quantify this incompleteness and correct for it. And so as I turn to the science questions, we understand our completeness and have corrected for the objects where we were unable to measure a redshift. I'll show you error bars that include those incompletenesses. Okay, so back to the science questions. I had posed 2 questions at the beginning of the talk, one on cosmology, one on galaxy formation. So let's first focus on cosmology, and then we'll move to galaxy formation. So the first question is, what can we say about dark matter and comparison to simulation using the satellites around these Milky Way analogs? And so here are results from paper 2 from the 36 hosts. But again, in our full sample of 100, everything that I will say in the next 2 slides holds for that larger sample. So first, just some statistics. In our Milky Ways, we find between 0 and 9 satellites for each of our Saga targets. This is in comparison to Milky Way, which has 5 satellites to the same magnitude. What's interesting about these satellites, first of all, there's a large, scatter. What's interesting is that the number of satellites correlates only modestly with its host luminosity. So here's host luminosity and then versus satellite number. You can see there's a mild correlation, but it's not particularly strong. What's actually stronger is the brightness of the brightest satellite correlates with the number of satellites. That is, you can see this is kind of a beautiful rainbow. This is a rainbow because the reddest luminosity function has both the most satellites and the brightest satellite, whereas the blue or purple systems have its brightest satellite is fainter and there are fewer satellites. And so that's really quite interesting and something that we can really test in the simulations. The Milky Way sits kind of right in the middle of all this. The dotted line here is the Milky Way's luminosity function. The Milky Way is consistent with being drawn from the Saga luminosity function. That is, there's a huge amount of scatter in the Saga systems that we see, and the Milky Way is consistent with being drawn from that scatter. Turning that question kind of around, we can ask, what do the simulations predict? And is Saga consistent with those simulations? And so here is the simulations. These are simulations from Yao and Ethan Nadler, taking n-body simulations and then a semi-empirical model, satellite model, and then taking the satellites, number of satellites and the number of hosts with that number of satellites using the Saga selection. So that is to say, the predictions are that there should be a fair number of satellites, a fair number of Milky Way systems that have 0 satellites. It should peak around, most of our systems should have 3 to 4 satellites. And then we should see a fairly small number of hosts that have larger than 8 satellites. Here are the Saga data. And so we do have systems that have 0 satellites. Most of our systems peak right around where the predictions suggest, and then heading out here. So the reason there are multiple symbols is that the lower symbol is the number of satellites we detect, and the stars is using that incompleteness correction to correct for our incompleteness. And so the conclusion here is that the Saga systems are broadly in agreement with the simulations. And again, this is holding with our larger sample as well. I'm going to actually skip this, but the Saga results are mostly in agreement with simulations from hydrodynamical simulations as well. Just briefly commenting on the radial distribution of satellites. So that was just the number of satellites. We can also look at the distribution of satellites away from its primary host. This is a bit of a busy plot, but this is the cumulative number of satellites as a function of projected radius away from the host out to the virial radius of 300 kiloparsecs. The green, the solid green, is the average cumulative, or the total cumulative distribution for all Saga satellites, for all Saga systems. So that's here. And at least at first blush, the Milky Way, which is the red and the orange contours, the Milky Way appears to be quite an outlier and is much more centrally concentrated as compared to the average Saga system. However, if we plot the quarter of the sample of Saga that is the most concentrated, that is the 25% most concentrated Saga systems, that is the green line here. And so the Milky Way is the Milky Way is more concentrated than the average Saga system, but it is not really more concentrated when we think about the host-to-host scatter. So it's within the expectations from host-to-host scatter. That said, the Milky Way is more concentrated than the average Saga system. Okay, so that's just kind of quickly touching on some cosmology, turning the focus over to galaxy formation. Recall that the question that we were asking was thinking about what processes quench star formation in low mass galaxy, and looking at the number of quenched satellites versus star forming satellites. First, we have to define what a star forming versus a quenched satellite is. In Saga, at least in the first Saga papers, we defined a quenched satellite because we have spectroscopy. We can define it based on the H alpha equivalent width. So we define satellites as being quenched if they have less than 2 angstroms equivalent width in H alpha. We are refining that definition just a little bit for the next iteration of the survey to include galaxy UV detections. However, it really only changes a handful of galaxies. And so this H alpha equivalent width definition is really quite robust. If we use that as our definition of quenched, when we first were doing this survey, it was really quite surprising. We found that only a single satellite out of 26 satellites was quenched. So here is absolute luminosity, G-band, G-R color. And we had a single satellite that was quenched, and we're like, oh, that's kind of concerning. In the larger sample, we certainly found many more satellites that were quenched, but it's still a minority. And again, in our much larger sample of 100, we still find many quenched satellites, but they are a minority of the objects. One concern that's, maybe kind of an obvious concern is, well, if you are, you don't have many quenched satellites, perhaps there is a bias against finding quenched satellites. For the same stellar mass, a quenched galaxy will be less luminous, and you'd have to detect an absorption line versus an emission line. We are very aware of that. And one thing that you'll note is that the quenched satellites tend to be the faintest satellites. That is, we are robustly finding quenched satellites at the limits of the survey. and that most of our quenched satellites tend to be the fainter objects. So the majority are actually less than minus 16 or less than a stellar mass of 10 to the 8th. What's also interesting is that our bright satellites that are quenched tend to be closer into the Milky Way, have a smaller radial distance. And so quenched satellites are preferentially found at lower stellar mass and closer to their hosts. Just to kind of summarize that in a different way, here is stellar mass, and on the y-axis is the quenched fraction. The orange is in the Milky Way and M31, so that is most satellites are quenched, and as you get to lower and lower stellar mass, 100% of satellites are quenched. The green bars are the Saga satellites. What you'll see is there's two sets of error bars. The thick error bars are the galaxies that we detect, and the green is assuming that absolutely every satellite that we don't have a redshift for is quenched. And so you can see that even those light green error bars don't get into the Milky Way region. Again, with our larger sample, this is this satellite, this result is holding. And so the conclusion here is that the overall quench fractions for Saga is lower, that is more star forming than the local group. And this has some interesting implications. So here is a simulation, a hydrodynamical simulation. This is from the DC Justice League group. Again, stellar mass, quench fraction, so trying to do an apples to apples comparison. And the quench fractions were actually a little bit lower than the Milky Way. And so I think this will be a really interesting avenue to continue exploring. Okay, so just kind of looking on to the future and talking about what we hope to publish in the next couple of months. The data taking for 102 hosts has been complete. We are actively writing up those papers and exploring things. One of the things that I'm really hoping that we'll be able to do is move beyond these quenched fractions and get more subtle and start measuring. We're beginning to measure star formation rates to see where our star forming satellites lie on the star forming main sequence, to understand the stellar populations and do stellar synthesis for those quenched galaxies, and to understand the quench stuff a little bit more in more detail. And so the hope is to have a checkbox the next time I speak to you next to stage 3. We also have some really interesting results thinking about the future and moving beyond Saga. And so there's some really exciting work being done with DESI. So DESI is a 5,000 fiber spectroscope that has been operating at Kitt Peak now for the last 1.5 years. The data taking has been going incredibly fast. Risa Wexler is my co-PI on Saga, is leading a secondary fiber program on DESI using the Saga criteria, using the Saga cuts to find low redshift galaxies. The idea there is just to find low redshift galaxies at between 20 and 40 megaparsecs across the whole sky, agnostic as to what environment they're in. That data taking is amazing. We have something like 50,000 galaxies already using the secondary fiber program. There should be some really exciting results coming out of that soon. In addition, using the Saga data, John Wu at Space Telescope has developed a machine learning algorithm, a CNN neural network, to train and identify low redshift galaxies. And so those are also being targeted in this DESI secondary fiber program. And this is a student, Elisa, who's been leading that program. So let me just wrap up. I apologize, there's a lot of noise outside. Hopefully you can't hear that. So the first question I posed was, can the satellites around Milky Way analogs tell us something about dark matter? And what we have found is that the satellites of our Milky Way analogs are consistent with predictions of lambda CDM, which is reassuring, and that the Milky Way itself is consistent with being drawn from the Saga distribution. That is, the Milky Way seems to be relatively normal, at least in terms of Saga satellite luminosity functions. On the galaxy formation side, the question was, what processes, or what can we learn about quenching in low mass galaxies? And we have found that indeed the Milky Way is perhaps not normal in terms of quenching, that the Saga systems have many more star-forming satellites as compared to the Milky Way, and that this may be interesting as we compare to simulations as well. I will end there. Instead of leaving with my conclusions, I will leave with these images, which are really quite beautiful, although I guess they're behind me as well. I also want to thank the team. This is a very small team, and it really is a true pleasure to work with everybody that you see here. And so not only is it fun to do good science and get some cool results, it's good to do it with good people. And so I will end there.
Thank you so much, Dr. Geha, for the very interesting talk. We now have time for questions from the audience. If you want to ask a question, please just raise your hand and I'll call on you. And in the meantime, I will check if we have questions from YouTube as well. I invite our people watching on YouTube, please post a question and I'll direct it to Dr. Geha. Oh, we have a question from Rodrigo. Go ahead.
Thank you, Tassia. Thank you, Marla, for such an interesting talk. Well, I'm not an expert in this field. You showed at the end a slide about the quenching galaxies on satellite galaxies. What I'm not sure if I got it right is, do we have a correlation with quenching galaxies and their masses? Is that right? So if that is what the data is showing, what is happening? Shouldn't it be the opposite?
Yeah. So in the Milky Way and in more dense environments, we certainly see a correlation with lower mass galaxies being more quenched. The way to really understand it is looking in the field. And so I should have stressed that. Let me go back, see if I can go back. And I apologize, I hate when people do this, but here. So I should have stressed this. Thank you for the question. So if we look in isolation, so just purely isolated galaxies at the same stellar mass, that's what's shown in purple. So in purple, these are results from Sloan. And what we see in the field is that the quenched fraction of isolated galaxies is higher mass, and then drops, and then below about 10 to the 9th, so that's roughly LMC, every single isolated galaxy is star forming. Another way to say that is galaxies by themselves cannot self-quench, at least down to where Sloan could probe, which was about 10 to the 8th or so. And so what that means is that at least in this interesting region here between, let's say, 10 to the 8th and 10 to the 9th, galaxies are in the field, they don't self-quench. They come into a Milky Way environment, and it's environmental effects that is quenching those galaxies. What that environmental effect is, whether it's ram pressure shipping or triggered star formation and enhanced star formation, and then they turn off, we can't yet say. And that's why I really want to look at the star formation histories and the star formation rates in the satellites. And so whatever is quenching those galaxies, quenching the satellites, can't have been an internal process, because if it was in isolation, it would still be forming stars. What's happening below 10 to the 8th, 10 to the 7th is very interesting, and could be that even in the field, this quench fraction goes up. And I think that's something that LSST, in combination with some of the deep spectroscopic surveys, will be able to tell us. But that's kind of where hopefully my research group is heading.
Okay, now I got it. Thank you very much.
Are there any more questions from the audience? Okay, I have a question. Okay, so I think there was a plot that you showed. It was one with like a shaded region, and then you had like several points. I guess I didn't write down the name of the. Can you?
Star formation or?
No, it was before. I think it was before.
Later or before? I can keep going this way. This one?
Yes. That
awesome.
one. Okay. Right. So I'm wondering about this trend here. Like, is it supposed to the green dots supposed to follow a specific trend? Because they seem to be going the other direction now compared to the LG dwarf.
Oh, so so part of it is just to get statistics to understand. So this is surface brightness and absolute luminosity. The expectation is that the lower intrinsic luminosity galaxies have lower surface brightness on average. And so if I plotted sort of more massive galaxies are going to have higher surface brightness, at least on average. The Milky Way, it's, there's sort of, this is such a small range that it's, I think, kind of hard to see as well. But in general, the lower luminosity galaxies tend to have lower surface brightness. And, that must have to do something with the efficiency of star formation, and the potential well in those objects.
So what we're seeing is the expected behavior.
Yeah.
Okay. Because I thought there was something off here. Okay, thank you. Can I ask another question?
Sure.
So I'm curious about the nature of dark matter, because I think this is such an open question. So you put that as an open question, but I didn't understand, but is this question being answered? Because you talked about it being consistent with Lambda CDM model.
Yeah, I guess I'm cheating a little bit. So it's, to say that it's consistent with Lambda CDM does not say anything really about dark, it does a little bit, right? But, it's certainly the warm dark matter predictions for the number of satellites. They're very, very different. And that's something that Saga can rule out. Everyone else can rule that out too. But, and so as we get to our larger sample, I think at least the number of satellites will be at least competitive with other indicators of CDM predictions. And then there's some other, sort of more subtle tests. So with Saga, we can also say something about the plane of satellites. So there's this, detection in Milky Way and M31 that satellites tend to be preferential around a certain axis. There may be like a plane or they're not randomly distributed in 3D space. And so Saga will be able to say something there about the distribution of satellites around Milky Way. And that again has, is another way to test at least dark matter predictions of lambda CDM. Really the nature of dark matter is, it's much easier to test in Milky Way satellites where you have individual stars and you can measure density profiles, and you can can do the dark matter annihilation tests and that sort of thing. So it maybe is a little bit of an exaggeration, but we are testing at least what the models predict.
I think it's exciting nonetheless. Thank you. We have time for more questions. Maybe if one of our junior members want to ask. If you're shy to open your mic, you can put it in the chat as well, and I'll read it out.
And if students are shy, they are also super welcome to email questions, and I'd be very, very happy to answer it. Just if we have a moment, I'm very excited. We have, in 15 minutes, I'm logging into another Zoom, and we are looking at hot off the press JWST images. And recording it because there was a news agency interested in seeing people's reaction to JWST images, which are absolutely beautiful. And I'm excited to see these images. Yeah, totally.
Will we be able to access it on YouTube, or will it be posted somewhere later?
I think it's something that they're folding into like a documentary of something. Like it won't be available like live, but the images will probably be up pretty soon. We have a Twitter feed and stuff like that, so we may post them there.
Okay, we'll be sure to check it out. So if there are no more questions, I think we can wrap this up. The presentation will be available on our website and on Linnea's YouTube channel. And I want to thank you once again, Dr. Geha, for the lovely presentation, and thank you everyone for attending. I hope you all have a great day, stay safe, and I hope to see you all again for our next webinar.
Guys, thank you too. I appreciate it.
Thank you very much.
Thank you.